So which end of this? Is this end over here, the donor? Let me do the laser point. I know, I can do it this way. Ouch. Is that the donor or the acceptor? That's the donor end, all right? So it's got to face an acceptor. An acceptor has to be oxygen or nitrogen, a lone pair thereon. Is that a proper acceptor? Yeah. So is this a proper hydrogen bond? Yes. Nicely done. Can I make, I see he's got some dotted lines off of those lone pairs on those oxygens. Can we make hydrogen bonds there? Ooh, I hear yes, I hear no. Yes. To the same part of water? No. Jack, can I write on yours? Yeah. All right, so let me, I think I got a pen. Yeah. What you would do, totally, that's wrong, sorry. Oh, wait a minute. Wait, it is. One of these days I'll get it right. Is that a proper hydrogen bond? Yes. I got a donor. I got an acceptor. Yeah, okay, it's a proper hydrogen bond. All right. Can I make a proper hydrogen bond here? Be sure? Yeah. You can't, that's right. Because why you can't? It's not special, right? It's not a proper donor because it's bonded to a carbon. All right. Questions? Yeah. So that's a good, can it form two hydrogen bonds to the same water molecule? I don't believe so. I think it's a geometry thing. Can it form hydrogen bonds to multiple water molecules? Like, could you have 3 water molecules hanging off of that? Probably. In real life, they might bump into each other, but in Bio 111, for sure, yes. Other questions? Yeah. A hydrogen, so the donor gives a hydrogen on an oxygen or a nitrogen. Right. And the acceptor has to be a lone pair on a oxygen or nitrogen. Right. Yes? Ooh, that is a super awesome question. Does that mean, let's be really specific. Take that one up there. Actually, scooch this down so I don't have to hurt myself stretching. All right. This water molecule, she asked, does that now mean there's only one pair on this oxygen? Yes. No. No. This is a great question. People always goof this up. If that was a covalent bond, well, then there'd be a problem, right? Because that would be hydrogen making 2 covalent bonds. So the answer is, and this is really important, people make this mistake all the time, that lone pair is still there, all right? And you don't get to say, wait a minute, that oxygen is making 3 bonds. It's making 2 covalent bonds and 1 hydrogen bond. So the oxygen's still happy. Oxygen makes 2 covalent bonds. It can make any other bonds you like. The count for number of bonds it makes is 2 for a covalent bond, so it can make a hydrogen bond, and that does not affect its covalent bonds or its lone pairs. So that's actually a really important thing. This is not a covalent bond, so it has nothing to do with the number of bonds hydrogen can make, the number of bonds oxygen can make, or stealing any lone pairs. It's not a covalent bond, so it doesn't change this thing. But that's another really important thing that people goof up. Other questions? Okay. Well done, everybody. I got a little more to say. Alex, thank you, sir. All right. So let me do this carefully. I'm sorry, Jack. I got your name wrong several times. Jack, thank you. Uh-oh. Computer, laptop. Turn this off. Uh-oh. Oh, no. Oh, doom. Why is my computer not responding? Well, that's what I get for writing on Windows. Oh, dear me. Uh-oh. Oh, this. There we go. Now we're making progress. Oh. Oh my. All right, and it is respond. Yes. Thank you. Thank you, Bill Gates. All right, fine. So we can make proper hydrogen bonds to water, just to fill those in. And we can make hydrogen bonds to water over here. All right. And benzoic acid, there's lots of possibilities here. There's a hydrogen bond up here to a HOH. And there's 3 lone pairs on here, so you can make hydrogen bonds over to here. And this is an extra strong H bond because the O is a full minus charge. So this is an honest-to-God happy hydrogen bond too, because you got a donor and you got an acceptor. But the acceptor is like an extra bonus acceptor because it's got a negative charge. So it really pulls that in tight. So if you look at these guys, benzene is not soluble. Is phenol going to be more soluble than benzene or less? More soluble. It turns out phenol is going to be more soluble. You predict this would be more soluble. It turns out to be, in real life, partly soluble. And benzoic acid is very soluble. All right? And again, why is that? In this case, roughly speaking, the amount of phobic stuff is the same. We're just getting more and more philic. In benzene, there's nothing philic about it at all. In phenol, you add a little bit of hydrogen bond capability, so it's slightly soluble. In benzoic acid, same amount of phobic stuff, but you tack on this other thing that's really hydrophilic because it can make hydrogen bonds and it's charged, which is a major bonus thing as far as water is concerned. Questions about that? All right, so put this into practice on the clicker question, and then we will